Let's start with our discussion of the random forest classifier. So, random forests are a simple and effective way to improve the performance of decision trees. And if you recall from last lecture, we said that decision trees are a nice and interpretable classifier, but the performance is typically suboptimal in practice. And decision trees are a so-called randomized ensemble of decision trees by using an ensembling technique called bagging, which is short for bootstrapping and aggregating. And while decision trees are not that great in terms of performance in practice, random forests are actually one of the most powerful classifiers to date. Let's start with a brief recap of decision trees, and I won't go into detail here, so this is just a refresher. Please consult lecture 3 for the details of decision trees. So we had this motivating example where we start with a disorganized fruit basket containing all kinds of fruits, and then based on hierarchical decisions we would come up with cleaned baskets containing only one type of fruit. And essentially this amounts to a decision tree, so a binary tree containing decision nodes. So the internal nodes are these decision nodes asking questions about particular features of our samples, and then essentially we would classify a sample by following these decisions and then end up in one of these baskets or leaves, and then we would use the classifier within this leaf to classify our samples. And the basic learning algorithm of decision trees was this so-called card algorithm, which essentially is just a greedy, recursive tree-throwing algorithm. So we start with a single leaf, and we first assign all the data points to this leaf, and then we would sort out these data points to sub-leaves. So essentially this works by calling this split function on our leaf. And first we would consider a large set of decisions, so we'd consider all the features and several decision functions, and we would compute the so-called cost. And then we would go for the decision with the minimal cost, and recall that this cost was defined by improving the purity, so by checking whether the new leaves contain more samples of only one label, so we had several purity costs, and then essentially we would decide for a decision with minimal cost, and this split would induce two new leaves, L0 and L1, and then we would recursively call this construction again, so the split function. And we do this until a certain stopping criterion is met. And again, please consult lecture 3 for the details, so this was just a quick refresher of decision trees. And well, as mentioned, decision trees are really nice and interpretable, but they don't perform too well. So the performance is usually not top in practice. However, so the random forest essentially just takes a lot of decision trees in an ensemble and is actually one of the strongest classifiers to date. And to wake your interest for ensemble methods, there's a huge success story in history. So like 15 years ago, there was this so-called Netflix competition where the goal was to increase the recommendation engine of Netflix by 10%, so matching movies to potential customers. And in the end, so people competed, and the race was close, and in the end, different teams would unite and actually come up with an ensemble technique. So an ensemble technique finally won this competition. And ensembles are also frequently motivated from the so-called bias-variance trade-off, which I will just briefly describe in a nutshell. So recall that our training and test samples are actually randomly drawn from some distribution. So we called this P star in the last lecture. And since the classifier is trained on the training data, which is random, also the classifier is a random variable, and therefore also the train and test performance is a random variable. Now figure that we could now draw repeatedly train and test sets, then we would every time we get a new training set, we would get a new classifier and therefore also different performance. And if we now do this experiment and draw 200 different train and test sets, and at the same time we play with the model complexity, so figure the example which we had last time, that we would increase the degree of polynomials, or in general the number of parameters in our machine learning model. So we would increase the model complexity and then check what happens with the training and test error. We would get some figure like this. So with increased model complexity, the training error, so the blue line here is the training error, just goes down, down, down. And the test error would actually go down in the beginning, and then it would increase again. And this is often explained by the following phenomenon. So if we have a more complicated model, then, well, we will have higher variance. So like, because the model is trained by the training set, by training on the training set. But if the model is too flexible, it will have a high variance. So the classifier will have a high variance, and therefore also the test performance will have a high variance. So if the model is really simple, so we need little data, and we will have a low variance. But if the model is complicated, so it has a lot of freedom, we will have a high variance. So in general, this phenomenon of overfitting is often explained that simple models have low bias, or no, a high bias but low variance, and complicated models have low bias because then it can actually approximate the true classifier, the base optimal classifier arbitrarily well, but they will have high variance, and essentially at some point the variance begins to dominate and we will start to overfit. So, but the motivation for classifiers is now essentially, so if variance is the problem, then we could actually do the following. So we could now just repeatedly train classifiers n times and just average them. And therefore we would actually reduce the variance of the ensemble classifier by n. So the more classifiers we train, the less variance we have. However, there's a fundamental problem. We cannot do this because we only have one training set. This actually would require that we have n different training sets, which we don't. So this is nice and good, but actually where do we take these different training sets from? So where do we take multiple training sets from and therefore train multiple classifiers? So while this is in principle not possible, there's a technique which actually kind of simulates this in some heuristic sense, and this is called bootstrapping. So bootstrapping is not only known in machine learning, but actually a well-established statistical analysis method, and it's more generally used to estimate noise distribution of mean of estimators. For example, of mean estimators. So figure, for example, that you want to measure the average, the mean height of the world's population. So you would select maybe 1,000 people from the world's population. You would compute the average, but since you took a random 1,000 people, if you take another draw of 1,000 people, then you will get a different mean result. And essentially to estimate how your mean estimator actually, how the noise of your mean estimator is actually distributed, you can use bootstrapping. So essentially, let me explain the idea of bootstrapping. So say we have a data set of n samples. So here this original data set of n samples. So here n is 10. So we have n samples. And now essentially the idea of bootstrapping is that we generate k new data sets. So a collection of new data sets, also all of the size n, by just sampling with replacement. So here, for example, we construct a bootstrap 1 by simply picking a random sample from the original data, say x7. We pick another random sample, x8, and we do this with replacement. So at some point we would pick maybe x10, but then again x8. So duplicates are allowed, so we sample just with replacement, just sampling with replacement. And we do this several times, so in general k times, and we will get different bootstraps. So all these will be now different data sets, all of size n, same size as the original data, and potentially and typically with replica. So like here we have x10 appears 3 times, and it can be shown that for large n, so each bootstrap, so we call each of these artificial data sets we call a bootstrap, then will typically contain 63% of the original sample. So we will have some variability. Now, going back to this example where we want to compute the noise distribution of the mean estimator, we would simply compute the mean of each of these guys here, and then we would get a distribution, so an empirical distribution of the means here. And this is often used to say, well, this is probably somehow related to the actual distribution of the mean estimator. This is in general, it works well in practice, but it's actually a bit of a heuristic. So there are no guarantees really that this distribution of the bootstraps will be really close to the actual distribution of your mean estimator, unless if you have really many samples. But generally, it's observed that this really works well in practice. So this is actually, bootstrapping is actually a technique from statistics, and in machine learning, this is often combined into bagging. So bagging means bootstrapping and aggregating. And the idea is very simple. So as in statistical analysis, we make k bootstraps, and now we train on each of these bootstraps, we train a classifier, and then we simply aggregate the results. So we either average the outcome of the classifiers or we do a majority vote. And we are not constrained to classifiers, so this also works for regression and other machine learning techniques. So really simple bagging is simply bootstrapping plus aggregation. And well, this already explains random forests. So random forests is really just bagging with decision trees. So we take k bootstraps, so sampling with replacement, and on each of these we run the CART algorithm. And in order to get a bit more diversity, so in order that the trees have don't collapse essentially to the same tree, so that we always decide on the first feature, we make also the tree growing a bit random. So instead of, let me go back to the algorithm. So here we compute decisions for all possible features and decision functions. And rather than doing it for all features, we now take a random selection of these features. So in particular, instead of taking all features, we take now only m randomly chosen features. And m is smaller than the number of features. So typical values are that we take about a third of the features. So each of these CART training algorithms is now also randomized by the variables it considers in each iteration. And then, well, in the end, this is just bagging with this slightly randomized decision trees. And then in the end, we just do a majority vote or do maybe an average of the classifiers. Typical values for the number of trees is like in the hundreds, so 100, 200, 500 maybe. And as said, the typical number for random features, or the number of random features, is like about a third of the original features. Well, this of course scales up the runtime, so we have now to evaluate k decision trees in order to average them. But since decision trees are rather efficient, this is actually in general not too bad nowadays. And yeah, this concludes our section. So we discussed bootstrapping, which is really a simple technique to do statistical analysis, but also machine learning. So we sample many data sets with replacement. That's called bootstrapping. Bagging is now a machine learning technique to bootstrapping, train classifiers on each bootstrap, and then aggregating the classifiers. So this is what I just said. And random forest is really just bagging with decision trees, where in order to diversify the trees a bit, we only consider m randomly features in each iteration. And as already said, random forests are one of the strongest classifiers. So in this paper by Fernandez de Lago, they investigated 179 different classifiers and 121 data sets. And then overall, the random forests were the overall winner. So this is mostly true for data sets which have not much structure. So we will, in a few weeks, we will discuss neural networks. As soon as your data sets have like signal, like structure, like speech, video, audio, natural language, then typically neural networks are nowadays the winners. But if your data sets are more tabular, unstructured data sets, then random forests are really top. And also Kagel's report 2019 reported that random forests are widely used. So like they are the second most widely used machine learning technique nowadays, and only second to simple methods like linear regression and logistic regression.